Today we're going to kind of segue off of our discussion of the sample proportion, and we're going to talk about the chi-square to test whether certain proportions are the same. This will be part one, and we will refine it further in a subsequent lecture to talk about the chi-square and testing whether data fits a particular model. Okay, so start off with a case study. An office has a candy jar that contains 35 Mary Janes, 42 caramels, 37 Tootsie Rolls, and 30 toffees. When the candy jar is refilled, it contains 30 Mary Janes, 15 caramels, 17 Tootsie Rolls, and 12 toffees. Are the differences in the proportion of the candy consumed due to more than random variation? Okay, right? Are people just sticking their hand in and pulling out a handful, or are they picking what they choose? Okay, and so let's start out with make a table. Okay, you have Mary Janes, okay, and caramel and Tootsie Roll and toffee, and we start out with the 35, 42, 37, and 30, and then we look at what's remaining at the end of the time: 30, 15, 17, and 12. And so this is the difference between this is the number of each candy that was consumed. Okay, and so this column, which we get by taking a 5 divided by 37, tells us that 16.7% of the Mary Janes were consumed, while 64.3% of the caramels were consumed. Right, taking 27, the number consumed, by the number we started with. 54 of the Tootsie Rolls, 54% of the Tootsie Rolls were consumed. And again, 18 divided by 30, 60% of the toffee was consumed. So here we have this proportion is different, but could it be just a random variation? Okay, the chi-square test provides a means of testing whether the obvious differences of proportion are significant. For the sake of argument, we'll take it as our null hypothesis that the probabilities, the proportions, are the same. We then can use this assumption to pool the data and estimate what the proportion of candy consumed is. We then use the proper proportion to estimate the values that we expect, and then we measure the degree to which our expectations are out of line with our observances. Okay, so pooling the data. Okay, we add together, there are a total of 144 pieces of candy. Of this 144 pieces of candy, 70 were consumed. So the proportion of candy consumed was 70 divided by 144, which is to say 48.6%. Okay, initially 35 Mary Janes were consumed. Our estimate is that 48.6% of them should have been consumed. Then we should have expected 35 or 0.486 of the 35 to be consumed, which is 17.010. Okay, we do for all the candies in the same way, and we summarize it in the table that follows. So we have our candy in this column, we have the number of candies of each type in this, we have the proportion assumed in this, and so in this case, right, we just put in the p hat for each of these, and then in this we put the expected number to be consumed here, p hat times n, and we put this number in. Okay, so now we measure how far out of line our expectations are from the reality. So we will let O, okay, and this is the worst variable choice ever, represent the observed candy, the candy that is observed to have been consumed, and calculate how far out of line it is with our expectations. This is the formula. Okay, the observed amount minus the expected amount, quantity squared, divided by the expected. Okay, so the Mary Janes, the 5 were consumed. We expected 17 to be consumed. We do, and then we divide by 17.05. We get our estimate 8.480. Okay, and so that's what's out. We do this for all of us. So we were like almost 8.5 out of line here. For the caramels, we were like 2.16. For the Tootsie Rolls, we were just very close. And for the toffee, we were very close. We add all of these up. Okay, we added this right here. Okay, saying we add up this entire column, and we get 11.634. That is how far out of line we are. The question is that too far out of line? Okay, the number above measures how out of line the data is with predictions. To answer whether it's too far out of line, we need another table. Okay, this is the chi-square table. Okay, we'll do alpha with 0.05% significance. We do degrees of freedom, which is the k, the number of categories, minus 1. So there are 4 types of candy, subtract 1. This gives us 3 degrees of freedom. And so where those two, the row and column, intersect, gives us that right there. So 7.815, and 11.634 is bigger than 7.815. We conclude the proportions are not all the same. So as a matter of fact, people are throwing those Mary Janes back. Okay, Angela, Bob, Carla, David, Ellen, and Frank are all playing tennis on the Wii. Each has the opportunity to hit 50 balls. Their results are enumerated in the table that follows. Test whether they are all equally skilled at a significance level of 0.05. Well, they all have the same number of tries. The numbers of hits varies here. Okay, and they're not all the same. The lowest one 38, the highest one is 47. But is that just due to random variation? Okay. Well, we pool the data. We add up the total of the N's and the total of the O's, and so we get 255 over 300. So that's, we expect 85%. Okay. We put that in a p hat column and run it all the way down. So we take N times p hat. That gives us our expected. Okay, and take our observed minus expected squared divided by expected. Just feed that formula right there and fill that in, and we do it this way on each of these, right? We'll calculate this by taking the 85% of 50, and so all of our E's are the same because all of the N's are the same. And we do the calculations for our O minus E squared over E, and then we add all of those up. Our chi-square test statistic being the sum of this, is 1.258. We have let's see, 1, 2, 3, 4, 5, 6 different categories. We have 5 degrees of freedom, and the table lookup for 5 degrees of freedom on chi-square is 11.070, and 1.256 is not greater than this, so everybody's doing about the same. Greg, Hannah, Ivan, Jody, Ken, Lydia, and Mike are all practicing for soccer. Each hits a certain number of balls towards the goal, and each scores a number of times. Their results are enumerated in the table that follows. Test whether they are all equally skilled at a significance level of 0.05. Again, we have the number of times they tried here, and the number of times they hit here. We pool the data. There were a total of 451 attempts. We had then a total of 278 successes, which means that as a group they succeeded 62%, 0.62% of the time, 0.62 fraction of the time. So you take this times the number of attempts, and we would have expected Greg, to have succeeded 29 times. We would have expected Hannah to have succeeded 38.48 times, and so forth down the table. We then substitute the O and the E into our O minus E squared over E, and get each of these numbers, and none of them appears to be too far out, quite frankly. The total sum, though, is 16.42. The table lookup for this many degrees of freedom, and it is 1, 2, 3, 4, 5, 6, 7, so 6 degrees of freedom, is 12.59, and 16.42 is greater than 12.59, so we reject our null hypothesis. We may not assume that all proportions are the same.